Great, welcome back. Today we're going to be talking about quantum query complexity. The idea behind quantum query complexity is actually, I think, kind of cool, because what it is it gives us a framework in order to answer many of the questions that we've been having about what the differences in power are between quantum and classical. So basically, the idea behind quantum query complexity is to figure out how many times we have to query a subroutine that encodes a particular problem instance or the information needed to specify a problem instance in order to be able to solve that class of problems. And the reason why we want to be able to take a look at this is that actually many of the natural algorithms that we solve on an everyday basis can be viewed in this exact same formalism. For example, a common case is, let's say we take a look at differential equations. So say we have the following differential equation. This is equal to, say, a linear differential equation, where this is some operator A acting on f of x over here. And what we want to be able to do is we want to be able to solve f of x as a function of time for this. Now, the way that this is specified is that often, if we take a look at the numerical methods for doing this, a subroutine is provided in order to be able to solve this problem for any a. And so, what we would do is, let's say we have a of x over here. We would have, the question is, how many times do we need to call a of x to estimate f of y, say, given f of 0. All right, this would be an example of a query problem. Now, the query complexity for this it ignores all other costs other than accessing A. So, for example, if we had some constant size calculation that's independent of A, or some even exponentially large calculation that's independent of A, that is not considered in the query complexity for it. However, and in such cases, if there were exponential costs behind it, then query complexity may not necessarily be all that great of a proxy. And so, to get an idea about this, the next thing I think that's worth asking is, why do we care? Why? Well, the first reason is that it acts as a good proxy for gate or time complexity, which this is really just a number of operations needed to solve the problem. Okay? Now, this is particularly relevant in cases like, say, the differential equation solver or other problems, like, for example, solving linear systems of equations, where a query to the fundamental subroutine that you're using is far, far more expensive than most of the other calculations that are going on. In that case, query complexity is really kind of, to a good approximation, going to tell you how long it'll take for you to run your code, be it quantum or classical. Now, the second reason is it makes comparisons between quantum and classical easier. Now, the reason why I say that is because of the fact that if you're taking a look at any sequence of gates, an arbitrary sequence of gates, there's many different ways that we could end up constructing a sequence of quantum gates in order to be able to implement some particular classical algorithm. And so that makes it very difficult for us to really be able to reason about what the right analog is between these. And in this case, all that we need to be able to do in the query complexity setting is we need to just be able to argue that a quantum black box, i.e. some subroutine that ends up giving us like A in this case, or whatever the arbitrary function is analogous to classical and make the same demands on input and output, okay? The other reason why this is, I think, kind of relevant is because at present, it's not really clear how we should best weight the value of quantum and classical computation against each other. At present, especially if we need to go through all the overheads of quantum error correction, the cost of doing a fault-tolerant version of a quantum algorithm is actually can be quite high and can lead to gates that are thousands of times slower in some cases than their classical versions. So figuring out, without looking at further details of the architecture, what the correct ratio is between quantum and classical costs is difficult. But in this case, because we've abstracted everything away but the queries, it's actually a lot easier to make that comparison, although it perhaps may not necessarily be giving us all of what we want. And the third reason is that good methods exist for proving upper and lower bounds on query complexity. Whereas in general, gate complexity is very, very difficult. In fact, actually, some of the biggest open questions in computer science are about comparing the time complexity of different classes of problems. And most of these big questions that we have actually don't have answers associated with them yet. And so I'm going to take a bit of a digression to go into this, because where query complexity sits in is that it actually does a decent job of answering many, or shedding light on also many of the questions that we end up having about computational complexity classes. So computational complexity classes, for the computer scientists in here, at least the theoretical computer scientists, this is probably old hat for you, but I figured for the rest of the audience, it might be good to remind you about computational complexity theory. So basically, the idea behind computational complexity theory is that what we want to do is we want to be able to deal with classes of functions. Classes or sets of functions of problems, I should say, that can be reduced, deals with classes of problems that are equivalent in cost up to polynomial overheads. So, for example, from this perspective, say we take a look at the cost of adding two numbers. So if we want to add n and m, and both of these over here are p bits, then the complexity for adding these two is order p. However, with multiplication, the number of gates that we need in order to be able to carry that out using schoolbook arithmetic is actually an order p squared. Okay, so these are equivalent polynomially because the cost of addition or multiplication is at worst case the square of what the worst case complexity is going to be for adding. So that is basically how we end up tracking it. Now, most of the basic complexity theory ends up dealing with decision problems. So basically, what we mean by a decision problem is what we want to do is we have a set over here of strings, say. And what we want to be able to do is we want to have a function f that maps this over here to just 0 and 1, where these are, say, no instances, and these are yes instances. So, for example, a bunch of problems that you're familiar with can be viewed as decision problems. A first one is the decision problem is prime. Okay, and this one will, for example, end up taking 5 and yield 1 because if this is a prime number, but it'll take 4 and say that actually this is composite. So that would be an example of a decision problem. And another example would be, is sorted. And so, in this case, we might have f of 1, 2, 3 equals 1, but f of 1, 3, 2 equals 0. So these are all examples of decision problems. Not all computational problems are decision problems, but most of the basic classes of problems that we're interested in computational complexity theory end up boiling down to decision problems. And so there's a number of different important classes in computational complexity theory. And again, the way to see these classes is that they act as kind of big signposts to give you an idea, roughly speaking, of how hard particular classes of problems are. The biggest class that we're going to talk about in this course is the class exp out here. Exp, this is the set of all decision problems solvable on a Turing machine using exponential time. So that's the biggest class. And actually that ends up encompassing all of quantum computing. In fact, actually, there's even a subclass of this that it turns out encapsulates quantum computing. And this subclass is known as p-space. And this is the set of all decision problems that can be solved on a similar Turing machine using at most exponential time, but polynomial space. Okay. Now, once we start getting beyond that, now we've got other more interesting classes of complexity theory. Inside P-space, we've got complexity class that many of you have heard of, known as NP. And NP, those are the set of decision problems that can be where yes instances can be validated in polynomial time on a Turing machine. Okay? Inside this, what we have is we have another class, which is BPP. Now this one is the set of all problems that can be solved in poly time on a non-deterministic Turing machine. So that is basically a classical computer that has some source of randomness. Now, if zooming in a little bit more, we've got inside BPP, we've got another class, P. Now this over here is as BPP, but deterministic. So there's no source of randomness whatsoever in this class P. Now, the class that's most interesting from our perspective is the class of known as BQP. Now, BQP is believed to sit inside this regime over here. And so what this class is a set of all decision problems that can be solved with constant success probability, i.e. something like success probability 2/3, on a quantum computer in poly time. I should also mention that in BPP, the same requirement ends up holding. We need something constant success probability like 2/3. Otherwise, you end up getting in this harder complexity class called probabilistic polynomial, which is quite powerful. So these are the broad stroke classes. And to give you an idea, basically, the way to think about this is that any problem in BPP can be solved by a device that's capable of solving all problems in NP in polynomial time. Similarly, a quantum computer, because BQP encompasses BPP, all such decision problems in that class can be efficiently simulated on the quantum computer or solved on the quantum computer within a desired success probability. However, one of the things that's quite interesting about this is the regions that we end up seeing in this graph. First is that at present, we don't know what the relationship between the complexity class NP is and BQP. At present, it's believed that BQP can give speedups for some problems that are in NP, but it isn't believed to be able to allow us to solve all problems inside NP. So that is the, for example, factoring is something that we can do on a quantum computer. So factoring is believed to lie, say, here. But it turns out factoring can't be mapped in polynomial time to every problem in the complexity class NP. It's in this complexity class called NP intersect co-NP. And so what that means is at present, we don't know whether or not all problems in NP can be solved on a quantum computer. And in fact, we believe in general that the answer is likely no. Similarly, we know that any algorithm, that any quantum calculation can be simulated in polynomial space. Any quantum algorithm can be simulated in polynomial space, but some of these problems are actually don't seem to really be solvable efficiently in NP. For example, there's many dynamical simulation problems where we're simulating physical systems that can be simulated in BQP, but is not known to be simulatable in NP. In fact, actually, P-space is the best complexity class that we know of for this. And so these end up giving us some good signposts. If we end up running into a problem that we want to run on a quantum computer, the coarsest understanding of how hard the problem is going to be is given by complexity theory. However, a big challenge with complexity theory is that there's just so many unknowns about it. So, for example, the things that are unknown, and all of these things it's unknown whether or not P is equal to BPP. Okay? So does randomness actually end up giving us an advantage or not? We don't know. We actually don't know whether or not BPP is equal to BQP. BQP. Meaning, we don't actually know in time complexity whether or not quantum computers end up providing any advantage whatsoever. Similarly, we don't know whether or not BPP is equal to NP, and we don't know whether or not BQP equals P-space. All of these questions are open. Well, it's strongly conjectured that that this is not true, and this is not true, and this is not true. We really don't know about the first one. However, formally speaking, none of them have been proven. The biggest result that we do know is that we do know that P is actually a proper subset of exp. So that at least is good. But unfortunately, the rest of these inclusions aren't really known. But we have enough evidence to strongly suspect, based on years and years of struggle at these problems, that some of these are unlikely to be true. So if we run into a problem that's NP complete, it's very, very unlikely that we're going to see an exponential speedup on a quantum computer based on these conjectures. So if these conjectures are true, then we can give up on such applications for an exponential speedup. Okay? And so, while this ends up giving us some, qualitative understanding of complexity theory, there's actually a lot of things that complexity theory obviously doesn't tell us. Like, one of the biggest questions is, what is the complexity of multiplication? In fact, actually, the matrix multiplication question is still open. And for example, multiplication, as I mentioned before, if you're multiplying two p-bit numbers, the school book algorithm will give you a method that goes like p squared. And it's actually been an open problem in computer science in order to be able to reduce the cost of this. And so actually, recently, is in like 2019, like within the last year or so, this actually has been reduced to order p to the p times log p. Okay, meaning that here the time complexity is upper bounded by a constant multiple of p times log p, asymptotically, and the limit as p goes to infinity. So what this ends up meaning is that these sorts of improvements, for one, these are not improvements that end up being seen in complexity theory. So while complexity theory can give us a crude understanding about it, it's not refined enough in order to be able to give us a detailed understanding of what the actual costs are for important subroutines. The other thing that is worth mentioning is that the proof techniques that are needed for this are, of course, incredibly challenging, which is one of the reasons why what we're going to do is we're going to not really spend so much time looking at complexity theory in and of itself, but rather what we're going to do is we're going to focus on this query complexity model because of the fact that rather than time complexity, we can actually prove things much more easily about the number of times such subroutines need to be queried in order to solve problems. So just like we did before, I'm going to begin talking about query complexity in a classical setting. Okay, so the query complexity specifically says that a user begins with a unknown function, let's call it f, that maps, I don't know, like 2 to the n. In this case, we're going to assume, for most of these query problems, we're going to assume that they're what are called binary oracles, meaning that they map the integers mod 2 to the n down to just 2 bits, which we can just think of as 0 and 1. Or sorry, 1 bit, which we can just think of as 0 and 1. Okay, the user begins with an unknown function. They have no knowledge whatsoever of what this function specifically does. It is promised, however, that f has certain properties, okay? So in this model, we're told when we begin that f will have some type of property, like, for example, it might have that there exists only one element that ends up evaluating to 1. Now, these properties we generally do, or assume we don't need to test. We have absolute confidence that the unknown function that's been provided to us has those properties. And the next thing is, we are not allowed to look under the hood at how f is implemented. So we're not allowed to introspect on this subroutine. And this is reasonable if, for example, we're designing an algorithm that's designed to run for any function that's provided to it. Because obviously, if we're designing an algorithm that isn't special purpose, what we're going to have to do is we're going to have to make sure that it works for every single possible subroutine. And so we can't compile in advance against that. And so that is basically what the setting is, and that the any info the user learns about f is from experimentation and each excess is costed. So for example, if we're running a particular program that, tries to learn some symmetry, for example, of f, as some component of a larger algorithm, we have to pay a price. One query for every single time that function is invoked. All right. So that is the basic setting for it. To give you an example, and this is an example that we're going to go back to, is let's look at the search problem. Okay. In this problem, assume that we've got an oracle, or a black box function, that maps z2 to the n to z2, such that for a value m in z2 to the n, so some particular bit string, f of m equals 1, otherwise f of x not equal to m equals 0. So you can think about this as a generalization of a search problem, or a search problem that has no structure whatsoever to it. We just have this function that says, is this the thing that we're looking for? Now, this is a very, very useful primitive because actually there's a bunch of problems that can be reduced to this search problem. For example, a naive approach to factoring can be done by searching. So, for example, how we would do this is we would say, okay, for two numbers that are that we end up putting in, can we find do those two numbers multiply together in order to be able to form the number that we're interested in? If so, then it's composite. So we can end up viewing factoring as a search problem for the two numbers that end up multiplying together in order to form the composite. So that is an example. And the claim I'm going to make, the search problem requires theta of 2 to the n queries to f to solve with 0 error probability. Okay, and here, just so to remind you of Bachmann-Landau notation, we say that a function is contained in the equivalence class a big theta of g if lim n goes to infinity of f of n over g of n equals a constant, and lim n goes to infinity of g of n over f of n equals a constant. So the way to think about this is that what this ends up saying is that a function f of x and g of x are big theta each other, for example, if asymptotically they're upper and lower bounded by the same thing. So for an example of this might be a function that could look like that versus that. So asymptotically, these two functions are the same. They approach the ratio approaches a constant as n ends up increasing. Okay? Now, let's prove this. So, proof. So the easiest one to do is the forward direction, the upper bound. So first, we say that there exists a classical algorithm that solves search in 2 to the n minus 1 queries in worst case. Okay, now this existence is actually really obvious. In order to be able to see this, let's imagine what we do for this particular problem is that we guess first 0. Then if this fails, then we guess 1. If that fails, then 2, so on and so forth, going all the way down to 2 to the n minus 1. If we fail, i.e. if f of 2 to the n minus 1 is still equal to 0, then we know from the promise problem that 2 to the n minus 2, f of 2 to the n minus 1 has to equal 1. So therefore, if we searched all but the last element, and they all aren't the thing we're looking for because we're promised that there's actually just one value, then this over here will tell us that the hidden bit string that we're trying to find has to be 2 to the n minus 1. And so therefore, this algorithm, in the worst case scenario, will end up requiring 2 to the n minus 1. If it finds f of x equals 1 with x less than 2 to the n minus 1, then this implies that we're good because it required less than 2 to the n minus 1 in this case. So worst case scenario, it requires 2 to the n minus 1, and therefore the query complexity here is in order 2 to the n minus 1, which is equal to order 2 to the n, because asymptotic notation doesn't care about constant factors. So that is the forward direction. Now let's take a look at the lower bound. Now there's many ways the lower bound can actually be proved, but we're going to end up using entropic arguments in order to be able to make this. So what we're going to do is we're going to ask, how much information do you end up gaining from each of those 0 measurements? So the way to think about this is, let's say what we've got is we've got n items. We have no knowledge whatsoever about which of these n items is the marked item. Okay? So without loss of generality, we can end up picking, say, the first one. All right? And let's say we apply this on f of x0 over here, where this is x0, this is x1, so on and so forth. And let's say this is equal to 1. Well, if it's equal to 1, then we're done. Awesome. But let's take a look at how much information we learn when we end up getting 0. Now, if we end up getting 0, then all we've done is we've eliminated this possibility. Therefore, we know that the marked item ends up residing in the rest of this range. So our probability distribution is a uniform distribution on 0 to n minus 1. And then we can end up envisioning this as a uniform distribution after we measure 0 to n minus 2. Now, we could take a look at the information gain, which is basically going to be given by the ratio of the probabilities that we have for this. And so this information gain over here is simply log base 2 of n over n minus 1. Okay? So that is the amount of information that we end up gaining from eliminating this one item. And this, as you can see, this would make sense. In the event that the new space that we have over here is half the size of the previous space, then we'd have log 2 of 2, which is 1. So we'd learn one bit of information if we can rule out half the items. And in general, because we're only ruling out 1, we get n minus 1 here. So this is the amount of information that we end up gaining, which we can end up writing as log 2, 1 plus 1 over n minus 1, which, of course, is order 1 over n. So we're learning a small fraction of a bit every single time we do this experiment and end up getting a 0 outcome. All right. And so then let's imagine what ends up happening as we end up summing this. So the worst case scenario is we're going to do this until we end up getting all the way down to the end over here. So if we do this, then the total amount of information that we end up getting by summing this m times is going to be at least sum over n equals 2 to m, the information gained in this, where this is I of n, and that is equal to the digamma function, which is a special function that you can look up, minus gamma, plus gamma minus 1, which from Wikipedia, if you look at the asymptotics of this, is less than or equal to log m plus 1 plus gamma minus 1, which is equal to log m plus some constant. All right, great. So m is the maximum number that that we basically end up needing to go up to for this protocol. So if m is smaller than 2 to the n, then the total amount of information that we end up gaining from all of these experiments is going to be log 2, and let's assume that it's smaller than this. Okay, and this, using Bachmann-Landau notation, means strictly less than, oh sorry, I meant n, which is equal to little o of n. Oh, and I should say plus O1, but the O1 is implicit in this. So we end up getting that. So this function requires strictly less than n bits in order to be able to encode m. So this implies if we had a protocol that made this happen, then any n-bit number can be encoded using little o of n bits, i.e. strictly less than n bits asymptotically. So for example, what this means is like log n or square root n. All of these things are in little o n. So if we end up having something that scales asymptotically smaller than n, we end up getting this contradiction. And therefore, we need, in worst case scenario, we need 2 to the n queries. Okay, cool. So what this ends up saying is that our bound is tight, that we need at most 2 to the n with the first algorithm we said, and then this ends up requiring at least 2 to the n queries. And so therefore we end up getting theta 2 to the n for the total complexity for this. So therefore we can solve this search problem using 2 to the n queries. Okay, so why did I spend all of this time talking about the search problem in particular? Well, the reason why is every problem in NP can be thought of as a search problem. So we can end up rewriting every problem inside NP as a search problem where the oracle ends up encoding all of the validation as well as the searching that's required in order to solve the problem. And so if we could do this with a query to this oracle, which tells us whether or not we've found the thing, which can be by assumption, done in polynomial time in the complexity class NP, then what that ends up meaning is that if search could be done in sub-exponential time inside this query model, then P would equal NP. So this ends up implying that any algorithm that gets an exponential advantage must use auxiliary structure that's not promised of oracle or remove it completely, i.e. tear apart the black box, look inside, and white box it. And so while we don't know whether or not P is equal to NP, there are oracle separations. So if we constrain the problems to work through an oracle like we did here, then in that case we can actually easily end up proving that there's differences between how hard particular problems in these classes are. And this indicates the strength of query complexity. It really gives you a good way to get a handle on what the complexity is of particular tasks without running into the huge intractabilities that we would get if we just looked at this through the lens of computational complexity theory. And so now that I've given this example, let's go forward and take a look at quantum query complexity. So in query complexity, again, what we end up having is we end up having some function which ends up mapping n bits over here to 1 bit is the simplest oracle that we can have, although in general we would have 2 to the n to 2 to the m. So in this case, we would have a function like this, but let's think about what the quantum analog is for this. And the quantum analog that we're going to posit is an oracle that I'll call OF. Here, we're going to assume that this is unitary, that there exists some unitary matrix such that if we end up getting a bit string encoding x, where this is x is in z2 to the n, i.e. it's an n-bit number, and we end up having a qubit down here, let's say c, and this whole vector is it's a complex vector of size 2. Okay, so then how this oracle ends up working is just exactly the same that all of the reversible oracles that you've seen so far end up working. We say that it ends up doing this. Now, of course, there's many different types of quantum oracles that can be assumed, and for other algorithms, we may need to make deeper assumptions about what the form of the oracle is. This one over here is a type of oracle that I like to call a bit oracle. And we're also going to see oracles that end up coming up later called phase oracles, where the information isn't output in a bit down at the bottom, but rather in a relative phase between the inputs. Okay, but this over here is a simple generalization of what we end up meaning when we end up invoking a quantum analog of a classical oracle. Okay, and actually, while we don't know what the difference between the runtime of quantum and classical algorithms are, there actually can be huge separations in the query complexity for solving particular problems. And the first problem that I'm going to show you that ends up indicating this is a problem known as the Deutsch Josza algorithm. So, let's see. Now this is interesting because of the fact that when we take a look at factoring, with factoring, there's no actual promises that end up coming in. So, well, nobody has succeeded in finding a classical algorithm that's capable of matching the performance of some factoring algorithm like Shor's. For the Deutsch Josza algorithm, we've actually got much more compelling reason to believe that there's a quantum advantage in this case, because we can prove that the number of queries that are needed to solve the problem quantumly and classically are quite different. In fact, actually, there's a super exponential difference between the two. So, let's take a look at the particular problem. So, the problem of in the Deutsch Josza algorithm is as follows. Let's assume that you're provided a function, and the function is a Boolean function that maps z2 to the n to 0 and 1. And there's f is promised to obey the following. Either, and you could see this as with probability 1/2, f of x equals c for all x, i.e. it's a constant function, or there exists a set S such that the size of the set S is 2 to the n minus 1, and for all s in S, f of s is equal to 1. So this is known as balanced. So what I mean by the balanced case is that half of the possible inputs that we could stick into the function are guaranteed to evaluate to 1, and the other half is guaranteed to evaluate to 0. Okay? And so this is the problem, and what we want is we want to decide whether f is constant or balanced. Okay, and claim Classically, 2 to the n minus 1 plus 1 queries to f are needed to solve the problem with probability 1. And quantumly, one query to OF, which is the quantum analog of this oracle, is needed to solve with probability 1. Okay, so in this case, this is actually even better than an exponential improvement in the query complexity, because what we have is we have 2 to the n going down to just 1. So this is a huge, huge advantage for this particular problem. I mean, it's a useless problem, don't get me wrong, but what its main purpose is to show us where the power of quantum computing ends up coming from, and what the difference between this quantum subroutine and this classical subroutine is in terms of the amount of power that we're assuming behind it. So, the proof. Okay, so we're gonna show that the classical case can be solved using 2 to the n minus 1 plus 1 query to f. Okay, and the way to see this is basically, okay, let's envision the worst case scenario, which is something that we do over and over and over again in these types of proofs. The worst case scenario is that, let's say what we do is we measure 2 to the n minus 1 times. And this is going to be super improbable for the balanced case, but let's say we measure 2 to the n minus 2 to the n minus 1 times and get 0 out. And this is without loss of generality. The argument would go through exactly the same way if we measured 1 all of those times. So let's say we measured 2 to the n minus 1 times and got 0. Well, do we know that it's a balanced function? Well, it could be constant, or all 2 to the n minus 1 samples could be in the set S prime, or the complement of set that evaluates to 1. Okay, so that is the, so at this point, we don't know. And because we've demanded that this problem be solved with 100% probability, like if somebody holds a gun to your head and says that that you have to answer this question 100% or else I'll pull the trigger, then in that case, you would say, well, I don't know, I need to query this one more time. And so, if you query it one more time, there's two options. If we do this 2n minus 1 plus 1 times and get 1, then this implies that it's balanced, because of the fact that we got 0 every other time, and if we ever measure two values that are not the same, because the function can only be constant or balanced, the function has to be balanced in this case. Now, if we end up doing this again, 2 to the n plus 1 times, and we evaluate the function on the next value and get 0 back out, then we know that it has to be constant. the reason why is because 1/2 of the values are 0, and 1/2 equals 1. Excuse my highly dubious math, but you see what I'm saying is that, yeah, half the total outcomes end up evaluating 0, and the other half evaluate to 1. So if we measure it one more time, because we've measured over half of them and we've gotten the same value, the function has to be constant in this case. So therefore, either way that 2 to the n minus 1 plus first experiment ends up turning out, then we know with 100% probability what the function is, even in the worst case scenario. So therefore, implies there exists an algorithm that needs 2 to the n minus 1 plus 1 times, and if fewer than this, there exists an input where 2 to the n minus 1 plus 1 queries are needed. So you can see how both an upper and lower bound is needed. So in that case, what we would end up saying is that classically, big theta of 2 to the n queries are needed to solve. All right, great. So classically, we know that we need an exponentially large number of queries. What about quantumly? So, quantumly. So first thing, let's just remind ourselves what the analog of OF is going to be. OF is just going to take an input x over here and some junk qubit down here, which will store the output, and map that to x and x plus c. Okay? Now, our algorithm that we're going to do for this is we're going to begin with 0. And I'll explicitly write in tensor n, so it's very clear what's happening here. Then we're going to begin with the ancilla qubit set to 0. Now, first thing we're going to do is we're going to flip it to 1. Then we're going to apply a Hadamard transform. Up here, we're going to Hadamard transform everything. And so you can think about this intuitively as just creating a uniform superposition over all the possible inputs. Now, we end up feeding this into our quantum oracle, OF. Now, what we do is we just apply, again, the Hadamard transform to combine everything back together, and then we measure in the end. Okay? And my claim is that if we measure z equals 0, it implies that the function is constant. And if we measure a result z out here equals 1, then this, or not equals 0, sorry, then this implies it's a balanced function. So if this claim is correct, then what we have is we have a single query or a single application of OF allows us to solve this problem, leading to, in this query model, a super exponential speedup. So in order to see this, let's just go through the algebra for it. So to begin with, we end up at this point over here producing the transformation 0 tensor n 0 maps to 1 over square root 2 to the n plus 1 sum over j over here j 0 minus 1. Okay, now what the minus 1 comes from the Hadamard transform on 1 at the bottom, and this is just a normalization factor. Okay, so now let's apply OF. OF, what it's going to do is it's just going to take the value of j and then XOR this bit over here with the function evaluated there. So we'll have f of j here and minus 1 exclusive or f of j there. Okay? Now, what we can do is we can actually notice something kind of cool, right? Well, what ends up happening is if f of j equals 0, then what this transformation ends up doing is it'll map 0 minus 1 to 0 plus 0 minus 1 plus 0 equals the same thing. However, if f of j equals 1, then it will end up mapping 1 to 0 exclusive or 1 minus 1 exclusive or 1. And that is actually equal to minus 0 plus 1. Or sorry, minus 1. So, in the event that f of j evaluates to 1 for some quantum input j, then the sign of this term over here flips. This is actually an effect that we're taking advantage of that people call phase kickback. And it'll have a profound impact on the probability of distribution that we end up getting for measuring j, even though the operation actually is kind of happening down here. So this is what we end up getting. And so if we note this, this is equal to negative 1 to the f of j, 0 minus 1. And so now we don't even need a piecewise statement to be able to do this. We can end up rewriting this sum using this observation as a sum over j, negative 1 to the j, or sorry, f of j, times 0 minus 1. Oh, and there should be a j here. Okay, now what we're going to do is we're going to apply the last set of Hadamard transforms here on the topmost qubit. So applying h tensor n on on this register over here ends up mapping us to 1 over 2 to the n square root 2 sum over z equals 0 to say 2 to the n minus 1, and sum from j equals 0 to 2 to the n minus 1. And this part over here is going to seem a bit like voodoo for the moment, but trust me, I'll explain it in just a sec. J dot z plus f of j over here, and 0 minus 1. Okay, so what the heck happened here? What I mean here is I mean the binary dot product between two vectors. So for example, if I had 0, 1, 1 dot producted with 0, 1, 0, this would be equal to 0 times 0 plus 1 times 1 plus 1 times 0. So just the ordinary dot product in this case. So in order to see this, let's actually just take a look at the action of h on k over here. So k over here, this is just a 1 qubit state. And I'm using this as a placeholder for k is either equal to 0 or k is equal to 1. Okay? But we'd like to algebraically find an expression for this, similar to what we did before. This is equal to the following piecewise vector. 1 over root 2 if k equals 0, and 0 minus 1 over root 2 if k equals 1. So we can end up writing this actually as 1 over root 2 sum over z negative 1 to the z k times z. And we can see that plugging in all of the possible patterns in for this, for example, if we plug in z equals 0, then we'll end up getting 0 and 0, both with a plus sign. If we end up plugging in z equals 1, if the input k was 0, then we have a positive coefficient, like we see here. If k is equal to 1, though, we would end up seeing a negative coefficient, like we have there. So this ends up actually matching the exact same form that we ended up seeing up here. Now, let's take a look at what we would end up getting if we have hk1 tensor hk2. This is just 1/2 sum over z1 negative 1 to the z1 k1 to the z1 tensor sum over z2 negative 1 to the z2 k2 z2. Grouping all of these things together, this can just be written as 1/2 sum over z negative 1 to the z dot k, because this over here, z dot k in this case is z1 k1 plus z2 k2. So this is negative 1 z dot k z, where I've just grouped these two together as a binary integer. So we can see inductively, carrying this out, that this statement is actually correct. So now what we need to do is we need to take this guy and continue simplifying. So again, what that result was is it was 1 over 2 to the n square root 2 sum of j equals 0 to 2 to the n minus 1 sum over z, the same, j dot z plus f of j z, and then some bit that we're not going to care about so much over here. All right. So now what we want to do is we want to be able to measure the probability of getting 0. Or, sorry, actually, let's make our life a little bit easier. Let's assume first f of j is constant. Then up to a global phase, this is equal to 1 over 2 to the n square root 2 sum over j sum over z negative 1 to the j dot z z 0 minus 1. Okay? And so what we want to do is we want to be able to figure out what's the probability here that z equals 0. Okay? That is just going to be, in this case, by definition, it'll be the probability that we can write this as probability of z equals 0. And if I call this bit a over here, given a equals 0, plus the probability of z equals 0 given a equals 1. Another way we could write this is the expectation value of the projector, but I digress. This is equal to, because both of those probabilities are equal in this superposition, this is just 1 over 2 to the 2n sum over j All right. Give me a sec. I think I made a mistake. Okay, no, I didn't make a mistake in my calculation. I'm sorry. So in this case, I skipped a step and went to probability. I should have just left it as a state vector over here. And in this case, we want to be able to figure out the coefficient of just the z equals 0 amplitude, which we can write as -1 j dot z 0, where this is equal to 0. Okay, and that's 0 minus 1. Now, if we carry out this sum, we end up getting just 1 over root 2, because all of these are 0. Sum of j of 1, 0, 0 minus 1. And that is actually just equal to 0, 1 over root 2, 0 minus 1. And now, using this rule of probability, we end up seeing that the probability of 0 is equal to 1. So with 100% probability, this qubit, when measured, will end up yielding the value 0 if z is equal to 0. And remember, here, this is implicitly 0 tensor n. Okay, so now assume balanced. So in this case, what we end up getting is that the probability of measuring 0, p of z equals 0, now can be written as 1 is proportional to the sum of j, -1 to the j minus, or j dot z, plus f of j, absolute value squared. So I'm just adding up all of these coefficients over here. And so this is proportional to that sum, which is equal to sum over j -1, or sorry, it's actually outside, squared, -1 to the f of j squared. And the reason why is that we're trying to figure out the probability that z equals 0, so z equals 0 here. Now, substituting that in here, we end up having, that 1/2 of all j yield 0, and 1/2 yield 1. Therefore, because half of them yield 0 and half of them yield 1, this whole sum is equal to 0. Implies that the probability of z equals 0 equals 0. Therefore, if we go back to the claim that we made earlier, that if we apply this quantum circuit and we end up measuring 0 out of it, then we know our function is constant, i.e. that'll hold with 100% probability. That alone doesn't imply that if we end up measuring 1 back out, or sorry, end up measuring 0, then there's no balanced input that could potentially end up yielding us. This calculation that we did below says that, hey, if it's balanced, we don't know necessarily what we're going to measure, but it will end up being ultimately something that isn't the 0 vector. So this shows that we can actually solve the Deutsch Josza problem with one application of OF, okay, versus the 2 to the n that are required before, giving us a exponential speedup. Now, it's of course worth noting that one of the things that is most unrealistic is, even though this ends up demonstrating a separation between quantum and classical computing, at least with respect to query complexity or with respect to an oracle, this doesn't actually end up telling us much about the relative power of this case, because with although if we demand that there be zero error in the algorithm, there can be a big separation between the two. If we demand probabilistic, or we demand small error probability, then actually we can end up getting solving this problem with far fewer randomized queries. And you can see this because if we ended up doing 2 to the n minus 1 queries for some large value of n, and every single time we ended up getting back a constant, then we would say, well, with overwhelmingly high probability, this is going to be a constant function, not a balanced function. And so when we allow small probability in here, the speedups actually become much less significant. And so this example in that setting is not really a strong motivating factor for the power of quantum computing. However, in this error-free setting, it's very interesting because it's one of the few known cases where there's a provable super exponential speedup with respect to query complexity. So that's how things go with this. Next lecture, what I'm going to do is I'm going to talk about quantum searching and show how to get to use searching in order to be able to solve problems, solve a search problem with a quadratic, not an exponential speedup. And then this is going to dovetail into techniques that I'm going to introduce for proving lower bounds for quantum query complexity in general. So thank you very much for your attention, and see you next time.